Okay, everybody, we're going to go ahead and get started. So it's my pleasure to present Dr. Z. Lee from CU Boulder today. He has a background in more hydrology, flood modeling type of realm, and seems like he's going to give us a pretty holistic presentation today, which is cool. So before starting at CU Boulder just this year, Dr. Lee was getting degrees at in Singapore and Delft for his master's, National University of Singapore, and then his PhD in hydrology and water security from University of Oklahoma, and then most recently working at Stanford for his postdoc for a couple of years. And right now he's an assistant professor at CU Boulder's Institute of Arctic and Alpine Research in their Civil Environmental Architectural department. And yeah, I'll leave that and take it away. Thank you.
Yeah, thanks for the invitation and thanks for coming. It's really nice to see you all here. And today what I'm talking about is trying to rethink what the flood research is from living systems to a foundation model. Before I start, I just wanted to briefly mention what I do with the flood lab at CU Boulder. I operate the flood lab under the SEARCH framework, which ACE stands for the source understanding. That means I wanted to understand the origin of those flood events, so that either from atmosphere, river, convective systems, trying to get a holistic understanding of where those flood events originated from. Then the second is the U stands for unifying models. I was developing physical flood models during my PhDs, and now I'm moving towards utilizing AIs and how we can integrate AI models in flood model research so that it can be sped up and operate in real time. The third R stands for risk communication. And traditionally, the risk communication is kind of undergoing the top-down approach, meaning that the only message you received from National Weather Service is basically from federal government or some officials. But I imagine a future of a more bottom-up approach where you have the social demographic profile of individuals and you have more personalized warning messages instead of a top-down approach where there's not many actionable insights when you receive those warning messages. And lastly, G stands for global sectoral evaluation, where I propose this framework to try to get a holistic assessment of flood damage, either from direct damage or indirect damage. And next, I just wanted to briefly set the stage for seeing that floods are probably the most damaging natural hazards. And this report published by Joint Economic Committee saying that the annual total cost of flood in the United States is over 180 billion a year. And you can see the breakdown for each sectors. In the majority is for the infrastructure damage, while you have substantial amount allocated for indirect commercial impact due to the downtime plays, like floods can disrupt the food supply chain and also your work time. Now let's just rethinking floods. Now I just wanted to ask, when we talk about floods, what are we talking about? First of all, you might talk about the severity of a flood event. Say that's 50-year flood event, 100-year flood event, or 500-year flood event. That appears frequently in any news media outlet sources. And this image just shows you the severity of flood. As you can see, the flood depths is, there's some car wrecks there and the road signage over there. And you can see the severity, the flood depths over that event. And we might also talk about the extent of flood. Here's Boulder 2013 flood, where you can see during the peak time, the main campus of CU Boulder being inundated by this flood event. But is that all? We're only talking about the flood peak time. But essentially, what I'm proposing here, flood is actually a living organism where it has several stages, just like our human beings. It has an embryonic stage where you can essentially say the conducive environment or the environment, the atmosphere brew those flood events. It also has a growth stage where you say the flood peaks start to rise and you reach the maximum flood peak. It also ages, like the flood recedes and finally die off. How do we measure the flood features and its whole life cycle is a kind of an open research question. In the past, people are focusing more on the flood statistical indicators such as the magnitude and frequency, while focusing less on the flood process indicators like the flashiness, which represents how rapidly the flood wave rises, and the peak stream flow, the duration of the flood from its rising point to its decaying point, and also area and depths. Now, this here is a survey of existing flood literature we have so far. As you can see, most of the studies focus more on these flood statistical indicators based on this survey, while less focus on the flood process indicators. So that's where we wanted to contribute and see the full cycle, life cycle of the flood events, so we can get a grasp of the damaging flood events and its composition. Additionally, as you can see, the spatial coverage of our study ranges from different continents, and the temporal coverage is from 1950 to 2100, has the longest record of the flood features. During this study, what we found is that floods are becoming flashier, which means you have a more rapid rising of the flood waves. It's becoming greater, meaning that the flood peak stream flow is becoming greater. And also the flood depth is becoming deeper and area is becoming wider, while you have reduced flood rising time and reduced flood duration. Now, this is for different scenarios playing into the future, and just looking at the typical hydrograph, and you can see the uncertainty band in this hydrograph. So this is a breakdown of global major river basins. We group them into different categories, where in the red category, you have all 4 indicators rising. And the orange ones, you have the ascent rate, the rising rate is increasing, flood peak increasing, and depth increasing, while the flood area is reducing. And the green area is you have the flood peak, stream flow, depth, area decreasing, while the ascent rate or rising rate is increasing, and so on and so forth. But what we found is that the majority of the global river basins, accounting for over 60 global major river basins, having 4 indicators increasing in the future. And we also attributed this increase to different flood types, as here showing you a typical way to classify flood events into intense rainfall-induced floods, excessive soil moisture-induced floods, snow melt-induced floods, and rain on snow flood events. And what we found is that rainfall-driven floods contribute significantly to the flood depths and area. So in this graph, I just grouped the rainfall floods and all other flood types together because they have a similar amount of flood events. The majority are still driven by rainfall flood events. Looking to the future, you can see the rainfall flood-induced floods are increasing in terms of the flood depths and flood area. Now, let's take a second, think about the flood modeling research, because I am a flood model developer, and where do we stand in those flood model development? I did a literature review of about 479 studies from 1970 to 2023. And what I found is that pre-2000, there were just a few studies working on flood models. And the primarily driven by those empirical and physical models. Now, from 2000 to 2018, there's a surge in physical models, as shown here. And between 2018 to 2021, that's a flourishing period for AI models. So you can see that AI is gradually taking off in our field to become a major part to replace some of the physical flood models. But there's an inflection point in 2021, where after which you see this decrease in the number of studies in flood model development. So we ask ourselves, is that the real situation? Like, is that due to the maturity of the flood model research, or is a decrease in productivity in our research after this COVID bump? So we observe that the number of studies are declining. At the same time, we observe the increase in flood impacts. We obviously constantly seeing those news media headlines showing there's 100-year floods, 1,000-year floods everywhere, but the number of flood studies are actually declining. Then we look at the limitations of current flood inundation modeling. Here just shows you the typical flood types that a model deals with. We have pluvial flooding, which is driven by intense rainfall. We have fluvial flooding, which is a riverine flooding generated by the very high stream flow and overbank flow. We also have coastal flooding that's caused by storm surge and groundwater flooding because of the rise of groundwater table. We also have human interventions or dams as well. Now, if you look at the existing flood inundation modeling, majority of them only does river flooding. And there's no pluvial, coastal groundwater floods or dam management interconnected to a suite of flood modeling software. And they are loosely coupled, meaning that if you want to couple the pluvial and fluvial floods, you normally would have to run a hydrological model to get the overland flow and subsequently run a hydraulic model or hydrodynamic model to get the flood inundation, the whole extent, and to get the riverine floods. And of course, many of them are not open sourced and they're user unfriendly and not easily visualized. So during my PhD, I developed this CRIS IMAP model to overcome these limitations. First of all, the CRIS IMAP model deals with pluvial flood. Here is an image of the simulation of urban floods in Philadelphia. And it also deals with fluvial flood and reservoir management. Here you can show this image by those overbank river flow inundating the coastal areas of Houston. It also deals with coastal flood, and here is a simulation of the coastal city inundated by the storm surge. Finally, it also accounts for groundwater flood, and here is example of the groundwater flood in those crop fields. So the CRIS IMAP really accounts for everything, all kinds of flood types altogether to produce a composite image of the flood damage, flood inundation depths, and area during those extreme events. Now, we can briefly walk through the processes in CRIS IMAP. So it is a coupled hydrodynamic model where it counts for you have the forcing data from atmosphere models or observation, that is precipitation, and it accounts for the land surface process such as evaporation, transpiration, etc., and goes through this variable infiltration curve to account for this soil infiltration and soil moisture in the land surface. And for the runoff generation process, it has the infiltration excess runoff where you get immediate overland flow, which is big contributions to flood. And also you'll get the saturation excess runoff, which is caused by the soil moisture excess runoff. And you also have the interflow from the soil layers to join to either exfiltrate to the surface water or just contribute to the groundwater and subsurface flow. And for the overland flow, we use two-dimensional numerical solutions to solve how water is redistributed on the overland. And it solves the two-dimensional shallow water equation, which is basically the mass balance and the momentum balance. And it adopts a finite volume numerical solution of governing partial differential equations. And it can go at variable resolutions as high as 1 meter resolution. And it accounts for semi-empirical groundwater model. So you can actually simulate the groundwater induced floods in those agricultural areas. So for the applications of CRISS-IMF model, what I've done is I have used that in a Hurricane Harvey event and also a flood adaptation mitigation study working with Alto Missouri tribal nation in Oklahoma. And there's a climate change impact looking at how the future floods in the United States will become. And also I will talk more on the urban hyper resolution flood forecast study in the next. That leads to the second topic of this flood modeling research, which is to propose a unified flood foundation model for the community to use. That is the adoption of AI. We probably will agree that AI-based flood models are fast, but there are several problems. One is they're not generalizable, meaning that you are trained for a specific event and only could work in that event. Or if you're trained for a specific domain, it's probably only gonna be useful in that domain. So how are we gonna generalize the AI-based flood models is a open research. And second, it's not trustworthy, meaning that because you don't have physical regulations on those AI models, and you probably will hallucinate or only just by memorizing the past flood events. While when you extrapolate that into the future, it might not work very well. And lastly, they're not open, because when I did the flood the literature review, what I found is the green-orange area accounts for the surrogate model or AI model. If you look at the open model, they only just a tiny proportion of the AI models are open. So in my approach, I produced a large flood inundation simulation benchmark or data set by simulating the physical model, the CRISS-IMF model over 10 cities, 20 domains in the United States. Here we picked those cities based on very diverse topography and climate and different land surface conditions, so that I want the AI models to learn what's the underlying physics and the different drivers of the floods. So we simulated the floods in San Francisco, Los Angeles, Oklahoma City, Dallas, Austin, Houston, Atlanta, New York City, Orlando, and Miami. So under the hood is this model architecture from general, like you've seen those weather foundation models or any foundation models, computer vision based foundation models. You have this vision transformer architecture under the hood. And for the model inputs, we're using the DM hyper resolution 1 meter LiDAR topography data and rainfall as forcing data, as well as some basin attributes like the land surface, land use, land cover, and soil properties, and also the slope of the basin, etc. So the final output is a flood depth. We're training this AI architecture to mimic what a physical flood model response would be. And we also attempted to address the model uncertainties because AI models, there are so many, there are variants of AI models. We wanted to utilize the expertise from every possible outcomes from this AI models. The one way to do that is by utilizing a mixture of experts, because we have different models like the CNN convolutional neural network based architecture. We have the vision transformer based architecture. They both have pros and cons. And the number here indicates the model parameter size, like the VIT 100 million, 300 million, etc. Those are the parameter sizes. And we use the random forest to kind of orchestrate how the different individual model responds. And collectively, we have these different experts to work on their prediction, and we have the brain to make the final call, like which model we should trust more under which conditions. Now, I'm just gonna show you some of the results produced by this flood foundation model, and we picked some out of sample testing sites. As you can see, it just have this on the left is the original image, and on the right is under this 100-year flood events. I will walk you through that pretty quickly, but before that, let's just talk about the positive side of this AI model as compared to the physical model. And as you can imagine, the obvious reason you want an AI model is the speed up. So it has over 800 times speed up as compared to those physical model, while retaining about 90% of the accuracy as compared to the physical models. And when we validate that against some independent flood database, here the blue bar shows the open source global flood models, GRC flood model. As you can see, the F1 score is pretty low, like 0.1, 0.2. But if we adopt this flood foundation model, that boosts the accuracy score to 0.7, around 0.7. And they are all based on those testing out of sample domains. Those cities have not been trained in my training data set. Then next, I will just show you how powerful this foundation model is. Let's just look at the prediction over the Los Angeles County here. Because traditionally, if you want to run a physical model, it would take years to complete a 1 meter resolution simulation of the flood over a US county. But now with this flood foundation model, it can be done within hours. Now, this is just an overview, but we can move closer when there's some patterns start to emerge. Move closer a little bit, and you can see those household streets, the neighborhoods, and as detailed as 1 meter resolution. So that really unlocks a lot of applications if you wanted to see the damage to your road network, to your houses, and your neighborhood, your backyard. That really can be helpful for you to make any decisions. And this just a scoping diagram of how we moved from a county overview to very fine grainy detail, granular scale of the flood inundation extent in your neighborhoods. All right, and the last topic I want to touch on is this automatic agents for flood modeling. Since we already discussed how we're going to advance the flood modeling, then we ask ourselves if there's a tool or agent can do the work for our humans. Because as you may nowadays you interact with ChatGPT, you can do the search of any topic, you can search for the weather, you can search for anything of your interest. But we ask ourselves if we can just automate the whole pipeline of doing a flood simulation using those agents. But first of all, we define the levels of automation in hydrologic modeling, just borrowing some concepts from, you have the self-driving cars, they have different levels of automation. I think L4 is where you have the totally self-driving without human intervention, just cars. But we define these levels of automation in hydrologic modeling, where L0 is where you have no agent. Basically, you rely on the human manual analyst, and you do the model yourself, set up the model, calibrate the model parameters, and do some fine tuning, write the reports, etc. And L1 is that where you have the agent as a process executor and user as an operator. And L2 is agent as a workflow builder and user as a workflow reviewer. L3, you start to see the more involvement in the agent as a decision advisor, and the human is a decision maker. And starting from L4, the agent, it will be a task delegate, and the user as approver. And finally, in the full autonomous level, agent will just execute all the workflow, and the user being just a monitor, observing what the agent is going to do. Now, I just want to play this video clip of our development.
AI agent.
I hope you can see
Plain
it.
language questions into complete hydrologic studies by finding data, configuring models, running simulations, and assembling clear results. And today, I'll walk through a flash flood analysis for Kerr County, Texas. I start on the home screen and launch the analysis. In the console, I select the reasoning model. Here I'm using GPT-4o. And in the prompt box, I type, "There was a flash flood in Kerr County earlier this July. Could you help me analyze this event?" Beneath the prompt are the data options. For precipitation, you can choose MRMS, IMERG, or HRRR. I'll keep the default MRMS. And then I click Run Analysis. As the job begins, Aqua sends the request to the model to parse location, dates, and intent, confirms Kerr County and the Guadalupe River system, and returns a concise location overview and hydrological context. It also surfaces recent news coverage on the July floods in Texas, which I open briefly to verify details. While in the background, the agent downloads the relevant data sets, clips the watershed boundary, and configures the CREST distributed hydrologic model for the July 10th analysis window. With inputs ready, we move into the interactive basin map. The red outline marks the watershed we're studying. Blue markers are USGS gauges, and red markers flag heavily affected hotspots such as Camp Mystic. I can toggle layers for elevation, DM, flow accumulation, and flow direction to understand how the terrain funnels water. Scrolling down to the precipitation views, you see an hourly animation for July 4th and an accumulation map for July 1 to 10. Colors from blue-green to yellow-red show increasing intensity. And the core sits squarely over the basin near Kerrville, exactly the kind of short, intense burst that routes quickly through the steep hill country network and triggers flash flooding. Next comes the hydrograph, produced by automatically setting up and running the CREST model with 2-minute MRMS rainfall. Black points are the USGS observations, and the red curve is the simulation. The timing aligns closely. The simulated peak is higher than observed, and the model reveals minute-scale structure that gauges often smooth, so you can see more detail in how the surge built and receded. To place the event in context, Aquawall plots the historical flashiness and frequency. The July 2025 point lands beyond prior observations, so the return period is labeled INF, meaning unprecedented within the available record. Scrolling further reveals the flood inundation view, which summarizes expected depths along the corridor and gives a quick sense of where water likely overtopped. Finally, the summary page collects the essentials, where and what we analyzed. North Fork, Guadalupe, near Hunt, July 1 to 10. What triggered the flood? A short, intense July 4th storm centered on the basin. What the river did? A rapid, record-level spike with good agreement and timing. And how rare it was, unprecedented in the site record, along with takeaways on improving peaks using denser rainfall inputs and local reports. All artifacts, basin maps, precipitation layers and animation, hydrographs, historical distributions, and inundation maps are organized in the results gallery for download. And Aqua also produces a polished PDF report that documents inputs, data sources, figures, metrics, and conclusions, ready to share with colleagues, emergency managers, and community partners. And to emphasize, the only input you need is the single plain language prompt at the beginning. Every other step is handled for you by the agent.
So that's what we imagine the future of hydrological modeling will be. Like you just only need a simple natural language prompt, then the agent will do this in the background and produce a nice report that can be interpreted by any person. Like if you don't have hydrologic knowledge, you can still run a model and produce this report, and you can, based on which you can make some decisions. So that's we built this platform, and it's open source. Just feel free to check it out. And this is a whole agentic workflow. And first you have the user query, and there's a flash flood event in Kerr County. Then under the background, the backend, the agent just download the data, do the pre-processing, and it also calls this hydrologic modeling, set up the model, visualize those results, and do some analysis, and finally produce a report. And it's a multi-agentic system where you have each agent is excel at one particular task. Like you have a context parser to find out the relevant flood event information for this, or also find out which catchment you want to do the simulation. There's a data retriever to get the necessary data from your prompt, and also some parameter, hydrological parameter initializer, and outlet selector, operator, etc., and report writer agent, etc. So those agents collectively produce the final report and analysis for any for you to interpret and produce support your decisions. Yeah, I think that's all I wanted to share for today. We can have more time for discussions, and happy to have your comments and suggestions, or just discussing on the collaboration in the future. But for takeaway for today's talk, I just wanted to remember that our flood model research is indeed at an inflection point where we have seen the declining in terms of the number of studies for research, for model research, and we really need to think big, think bold to kind of just to think with future directions that we want to pursue as a whole community to work together. And second, it is an era for disruptive science. If you think of our previous science is building on those increments, but with AI, with other different tools, technologies, it's time to think of disruptive science, how we really want to use those technology to advance this field. And with that, I will stop here and take any questions, and feel free to email me with your questions as well. Thanks.
Thank you, Dr. Lee. That was great. Yeah, we have plenty of time for questions.
I guess in the integration. So how does the integration of physical models and deep learning models will work for the futuristic stream flow, flood modeling, as well as for sustainable water management?
Yeah, so right now we're working on like acting AI as emulators to mimic the response from the physical models. But I can imagine you can also integrate some physical constraints into the AI models so that the AI does not produce some weird results. And also you can go back and check whether AI is making some reasonable predictions by enforcing some constraints to the AI models. I think that is a way to incorporate AI into this physical simulation. But also there are other ways like you can have more specific neural networks or AI models designed for solving particular subset of your models. Like if you're using a physical model, you say this numerical solution, the solving those partial differential equation is time consuming. I can replace a certain part of that physical model with AI models, just to significantly speed up that process instead of just replacing them as a whole. You can have more guardrails of AI models. Yeah.
Now we have a kind of an institutional setup. It actually goes back to the 1960s and floodplain mapping, flood insurance, everything's kind of set in place. How would this new technology disrupt all those previous institutional setup we had?
No, we're not just encouraging you to disrupt everything that you have done in the past. I think there's a way to, I mean, that's just a philosophy that we need to think things out of the box, not just, because our previous research is built on increments. Like if you look at the flood research, what has been done, and there's a little marginal increase that you can build on those previous research or increments. Now we're just trying to have an idea that if you can think out of the box and see how we're gonna incorporate those technologies that better inform our decision or just to produce the results faster than before. That's the whole point of it. But I didn't mean to just abandon everything have done in the past. And there's still useful information, useful knowledge, and those context gonna be useful for, let's say, if you're using AI models or anything, there's still fundamentals you wanted to build your AI models on. And those flood plains management are very essential technology or local knowledge that can be utilized by the AI models. So I don't think that's one way or the other. It's more of a combined use of local knowledge and those modern technology.
So given the sort of well-documented propensity for LLMs to make mistakes, do you think there's a danger inherently in a tool that's so simple, produce a report like this for a lay person's eyes, when there could be mistakes embedded in that sort of whole entire workflow?
Yeah, I do believe so. Because we do need maybe like regulations on the AI models, because nowadays the AI models can hallucinate, or even if you chat with ChatGPT, because they don't have domain-specific knowledge, they can just produce some weird results where it's not physically grounded. So I do think there's more work to be done as a community to enforce some constraints to the AI models, and also just to have it output its like reasoning steps, not just giving you the results, like what the LLM is thinking under the hood by unboxing the internal weights. And I see a future of the joint expertise from, you have the hydraulic knowledge, and also you have some AI knowledge that knowing that AI can hallucinate and how AI large language models operate, and jointly you can have that. But I mean, in the future, the full autonomous world is where AI has those regulations and produce reasonable output, and the human can trust it. But we're not even close to that future. But I think I do believe that that's a future to go.
In your physical model, I'm curious for the groundwater floods, like how long of a simulation do you have to run to capture some of that? Or is there some sort of like boundary condition that you use to run a shorter simulation?
Yeah, so far it's a conceptual groundwater model, but it's supposed to run in bounces instead of typical flood event, which usually occurs in days, right? You do need a long-term simulation to capture that groundwater flood event. And it's essentially the interaction in the subsurface. You have the interflow, you have the rise in groundwater, and how that exfiltrate to the surface water and interact with surface water conditions. It's interactive and long-term simulation, and it can be simulated because you have the both components from hydrologic modeling and hydraulic modeling together. You can simulate the response from those groundwater flood events. And I do want to point out that groundwater flooding is like underappreciated event because there are increasing number of groundwater floods. Like last year or 2 years in Argentina or South America, they have huge groundwater caused floods. While there are not many studies working on groundwater floods, I do think that's a future some research area needs to be paid attention to.
So you run, I mean, yeah, I'm curious, like, do you have to run the simulation for years or like a couple months or what have you, just for the cases you looked at?
Yeah, if you wanted to run that for that event, you can run months, but have to provide some boundary conditions, like you have the soil moisture, like antecedent soil moisture, or just groundwater level from other analysis data or any conditions that you can produce. Then as a boundary condition, you can run that for specifically for that event. That will be easier to simulate, but you can also run that for years. That will be more time consuming. Yeah.
I have a similar question. I had a question about computation speed.
Mm.
If you're doing a physical model, like LA County,
Mm.
at 1 meter grid cells,
Mm.
solving finite volume,
Mm.
how long does that take computation?
It will take years. It's huge because that's, I think LA County, that's a rough average size of maybe tens of thousands square kilometers. And if you think running a 1 meter resolution, that's equivalent to 1 second in real time to compute that, to advance one second in real time, that's equivalent. Then if you count for like 6 hours of flood event, I mean, I haven't done that test. It sounds impossible to do that.
So you do this on like on a gray or something?
What's
I
that?
assume you're not using Mike's laptop.
No, I mean, just on the HPC with several nodes, computing nodes, like 16 cores or 32 cores, is still very computationally expensive to run the physical model.
So practicality maybe not quite there yet.
No, and I do see there's a bottleneck in those CPUs because more slower or like there's a constraint. You're not advancing those CPU computing efficiency speed as much as you have this advanced GPUs or those different graphic processing units. Yeah.
I imagine you haven't done this follow-up work, but I just have to ask because I'm very curious. So you showed this plot where you had sort of this peak in 2021 of the number of flood model development studies.
Mm-hmm.
And then it decreased in 2022, 23.
Mm-hmm.
Do you have any sense that that trend has continued in 2024 and 25?
Yeah, that's a good question. I didn't look into that, but I guess that's the case because if you imagine the flood model development, it has been there for at least 5 or 6 decades, right? It's a very mature field. The models are there, and the fundamentals we're solving, the shallow water equation or Navier-Stokes equation, they're there for hundreds of years, right? We're not advancing it very much. It's just how we make our models more efficient, etc. And because of the bottleneck in the CPU computing, I don't think there's much work you need to do optimize your model. I can imagine that's still gonna be declining in the recent 2 years. That's why I think there's a like the room for some new technology to come in to kind of to have some incentives to contribute to the flood model research.
Good question too.
Oh, yeah, go ahead.
So on your training cities, they're very large, very populous, probably have a lot of data to
Mhm.
train from.
Mhm.
Do you like find, or have you tried running on more rural settings? And what do you think would be the, like, how far away in accuracy do you think it is from like running on Atlanta or New York City to run on, I don't know, like Fort Collins even, or somewhere more rural than this?
Yeah, that depends on like the simulation you have, and as long as you have those training data sets for rural areas, I think that should be on the similar scales as running in urban regions. But this study only focused on the urban floods because I think you only need that fine scales in urban cities, not that fine scale in rural suburbs, right? Because there's just not many flood damage to the infrastructure that especially you have different fine scale, micro scale infrastructure like the levees or any kind of structures that you have to simulate that at meter scale. So I think I don't see a justification to run 1 meter simulation in suburbs or rural regions. Otherwise, I think the AI models can pick it up as similar to the urban floods. Yes.
So I have a question, like when you're testing your model,
Mhm.
You talk about accuracy.
Yeah.
So what parameters you specifically look at to make a comparison for accuracy? Like, will you look at the inundation depth or inundation area? Because my understanding is that usually if your domain is larger,
Mhm.
that means that you will have more local accuracy might not be good enough. So you
Mhm.
probably go with the mean accuracy.
Mm.
So should be a choice between locally and the average one. So how do you get it?
Yeah, for that validation dataset, because we're using an independent observation based, it produced by the satellite data, this only account for the inundation area. So we assessed whether the model simulation agrees with the observations from the satellite, while the satellite has a coarser resolution at 100 meters. So we have to aggregate my 1 meter resolution to 100 meters to make that comparison. Yeah, I don't, there's a lot of things, details into the validation, how you report that, how you aggregate that. That's sort of the trade-offs, but we just show that our models is having like a superior performance than the existing global flood models. Yeah.
Gotcha.
Yes.
For your coupled models, have you noticed that there are specific types of flooding events that influence the model more or have changed, kind of baseline hydrologic models on their own? And if so, how do you see a more integrated coupled modeling moving forward that can account for these flashier events?
Yeah, it's definitely different types, like the models have sensitivities toward different types of floods. Especially if you're looking at flash floods that comes with a very fine scale, rapid rise your flood waves. And you do need first of all, you need a model to have higher resolutions to capture that fine scales. And it's a more I think the sensitivity is very large towards these flash floods, and especially you have very convective systems in this specific domain. I think there's a way that you can do more integrated coupling with, say, atmosphere models to capture that process. Because I think the bottleneck right now is how we frequently get those fine scale observation, precipitation data, or any data coming. You can use that to as your boundary condition to drive this coupled flood models system. So I think there's still a lot of work can be done to couple the flood models with the upstream atmosphere models and with downstream, like if you want to assess the impact of flood in terms of the economic activities, you can couple it with the economic model. You can couple that with a human mobility model, or so on and so forth. So there's a lot of rooms to be to develop your models having a more holistic assessment of how the flood is evolving, how the flood is impacting our society, etc.
I think we'll call it there. Let's thank Dr. Zealy again for his talk.